Welcome to the Explainer class. Today we're totally demystifying electrochemistry. We're skipping all that textbook fluff and zeroing in purely on high-yield exam logic and the specific numerical hacks you absolutely need to secure those neat marks. Let's dive right in. Now, I know electrochemistry can feel like a giant maze of formulas, but honestly, once you see the underlying logic, it becomes one of the most reliable scoring opportunities on your entire paper.
So, here's our game plan for today's masterclass. We'll start with a priority revision plan, then tackle conductivity and dilution, look at Kohlrausch's law applications, walk step by step through solving those tricky, neat numericals, and finish up by sweeping for the most frequent calculation errors. Let's get to it. Section 1, Priority Revision Plan. Let's crack this syllabus. To win, we first need to analyze our enemy, the exam itself, so you know exactly where to channel your energy for the maximum payoff.
Look, electrochemistry is going to throw 2 to 3 questions at you every single year, making up a solid 5 to 8% of your chemistry weightage. But checking out the data from 2010 to 2024 reveals something pretty incredible. You really don't need to memorize 100 different things. Mastering just 6 to 8 core formulas guarantees a massive return on your revision time. The absolute heavyweights here: the Nernst equation, Faraday's laws, Kohlrausch's law, and the relationship between standard Gibbs free energy and cell potential. If you hyper-focus your practice right here, you're literally halfway to full marks for this chapter.
Moving on to Section 2, Conductivity and Dilution. Let's lay down a solid conceptual foundation and look at the actual logic of what happens in an electrolytic solution when we just add more water. The simple underlying logic here is actually super fascinating. As concentration drops, meaning the solution gets more dilute, the molar conductivity actually goes up. Why? Well, think about it. Diluting a solution literally frees up the ions. It cuts down their attraction to one another and drastically boosts their mobility, which lets them carry an electrical current way more easily. So you're not just blindly memorizing a trend here, you're visualizing these ions finally getting the elbow room they need to move.
And that exact movement translates directly to a graph you're going to see a lot on the NEAT. When you plot molar conductivity against the square root of concentration, strong electrolytes give you this gentle, almost flat line. They're already fully dissociated, right? So adding water just slightly reduces that ion friction. But weak electrolytes, man, they show a sharp, dramatic spike at lower concentrations. All that added water forces them to suddenly ionize, releasing an absolute flood of new charge carriers.
All right, Section 3. Kohlrausch's law applications. Since we can't directly track that crazy sharp curve for weak electrolytes all the way down to zero concentration or infinite dilution, we desperately need a mathematical workaround.
And that brilliant workaround is Kohlrausch's law. It simply states that the limiting molar conductivity of an electrolyte is just the sum of its individual cation and anion conductivities. It proves that at infinite dilution, ions move completely independently of one another. So for strong electrolytes, we just extend that straight line we talked about right to the y-intercept to find our maximum value. Then we use those known ionic values, like puzzle pieces, to calculate the limiting molar conductivity for the weak electrolytes that we couldn't measure directly. Pure genius, right?
So how do we actually apply this under pressure on test day to find the degree of dissociation, or alpha? Well, by setting up a structured sequence on your scratch paper, you can crack this seamlessly. Step 1. Calculate your molar conductivity at the given concentration. Step 2. Use Kohlrausch's law to find that limiting molar conductivity. And Step 3. Just divide the first number by the second. It's literally just a ratio of how much it's conducting right now compared to how much it could conduct in a perfect world.
Let's jump into Section 4, Solving Neat Numericals. It's time to step up to the chalkboard and apply all this theory to a high-stakes numerical problem involving sparingly soluble salts. Notice the careful structure of this calculation for the solubility of a salt. Let's call it mx2. The problem hands us the KSP as 4 times 10 to the negative 12. So we carefully sub our ions into the KSP formula. For mx2, it breaks apart into 1 M ion and 2 X ions, right? That makes our equation KSP equals S times 2S squared, which neatly simplifies down to 4S cubed. By isolating S, we find the solubility is 10 to the negative 4 moles per liter. But wait, this is exactly where students freeze. The answer needs to be in grams per liter. Don't panic. We simply multiply that molar solubility by the given molar mass, let's say 120 grams per mole, to nail down our precise final answer. See? Structural logic beats panic every single time. Almost done. Section 5, Frequent Calculation Errors. Before we wrap up today's masterclass, we absolutely have to sweep for trapdoors, those super common mistakes students make when the exam clock is ticking.
Let's do a quick rapid-fire check to test your recall. When you're setting up an electrochemical cell, where exactly does reduction happen and which side gets the positive sign? Think about it for a second. Got it? Because if you calculate this backwards on the exam, your final voltage is going to have the wrong sign, and I promise you the exam setters will have that incorrect trap answer waiting for you in the options.
Just remember the classic mnemonic, red cat, reduction at cathode. The anode is where oxidation goes down, acting as your negative terminal, while the cathode is positive and handles the reduction. Keeping your anode and cathode signs straight, and always calculating standard cell potential as E cathode minus E anode is your absolute first line of defense against dropping really silly marks.
I want you to take a mental screenshot of this definitive checklist of exam traps. Number 1, swapping cathode and anode, which we just nailed. Number 2, never ever include pure solids, like solid copper or zinc bars, in your Nernst equation Q calculations. Only dissolved aqueous species count. Number 3, for Faraday's law, always write out the half reaction to find N, the actual number of electrons transferred, instead of just guessing based on the ion charge. And number 4, for goodness sake, check your unit conversions. If they give you current in milliamps, change it to amps. Time is in minutes, seconds. Do this before you even touch the calculator. I really want to highlight an amazing piece of advice from the East Saral IIT faculty. They point out that a student who confidently applies the Nernst equation, Faraday's laws, and the standard Gibbs free energy relation can score full marks on this chapter in under 3 minutes. This is a game-changing time management hack. It reminds us that while the questions might look intimidating, the underlying mechanics are incredibly predictable. By trusting the conceptual logic we've built today, instead of just blindly calculating, you conquer these formulas in a fraction of the time, saving precious minutes for those brutal physics or bio questions.
So let me leave you with this final thought. Armed with these strategies, you aren't just rote memorizing anymore. You are actively dissecting the exam itself. You see the traps, you get the visual graphs, and you have a rock-solid structural approach for the numericals. If you can break down electrochemistry this effectively, what high-scoring chapter are you going to master next? Keep this momentum rolling, apply this framework, and I'll see you in the next explainer.